there's a quorum here, I think. So I'll begin with a word of prayer. The mic is on, right? Okay. Dear Father, we thank you for this day, and just pray that you guide our steps. Lord, in your name I pray. Amen. Okay, so last time I shared with you guys the argument principle, which says that the logarithmic integral is equal to the difference between the number of zeros and the number of poles, counting, of course, multiplicity. And so that I think the argument principle 2 is really more where it's at. This is how we actually tend to use it, which says that the net change in the angle of f of z over the boundary of D is equal to 2 pi times the number of zeros minus the number of poles inside the curve that bounds D. All right? So this argument principle number 2 is that's the one we really use. And we're going to use that to prove Rouche's theorem in just a second. So this is Rouche's theorem. Did I zoom? Is it?
I mean, you can see it, but it takes up the whole
screen. I turned the thing when I... There we go. That way I can still write. So this is Rouche's theorem. Let D be a bounded domain with a piecewise smooth boundary D. And suppose F and H are analytic on D and its boundary. And we also want to suppose that H of Z is smaller than F of Z for every Z on the boundary. So I think of H of Z as being a quote-unquote perturbation of F. It's smaller than F. It's perturbing F by a little bit in such a way that it's never as big as F. All right? But that's, I mean, it could almost be as big as F. That's a pretty big perturbation in some sense. Actually, when I think of perturbations, I think of much smaller things being added. But, you know, in some sense it's that. And anyway, then, here's the punchline. F of Z and the perturbed F of Z plus H of Z, have the same number of zeros, counting multiplicity. This is like super nice because if you can take something complicated, right, and look at it as being the perturbation of something simple, thinking of F of Z being the simple thing, then if you can count the number of zeros or poles for the F of Z, then you've also counted the number of zeros or poles for the more complicated thing, which is really fantastic, yeah.
How do poles play into this? Do you just like include it? Or like...
Oh, did I say, I shouldn't be saying poles right now. You're right. My apologies. Good point. I'm still thinking back on the argument principle, and I should not say poles right now. Thank you for the correction. Okay, so let's assume that we've got the conditions of the theorem met, and we don't have a zero for F on the boundary of D, which means, of course, F of Z is non-zero. And can you see why it follows that F of Z plus H of Z is non-zero? What if there was an H of Z such that F plus H was equal to 0? That would mean that the modulus of F of Z is equal to minus the modulus of H of Z, which would be where equality. So we would violate the terms and conditions, namely that H is smaller than F if we had a 0, right? So that's a reasonable assumption. And consequently, we can also look at F of Z plus H of Z like so, factor out the F, right? Factoring out F, I've got 1 plus H over F, right? But H over F is something that has modulus less than 1 because this implies that, right? And therefore, the real part of 1 plus H over F has to be positive. See, because if this has magnitude less than 1, then certainly it can't have a real component, which is negative and smaller than 1. So this can't possibly be canceling. This has to be a positive quantity in the real sense. The real part of it has to be a positive quantity. Of course, there could be a complex component to the quotient of H and F, right? But focusing on the real part, we find that the real part is positive. And if the real part's positive, that means that this can't be 0, among other things. But more to the point, actually, that's not really what we're after. This being positive means that 1 plus h over f fall into half plane, which permits a single valued argument function throughout, right? So like, let's see here, 1 plus h of z over f of z, if I was to plot this equals to w, then the values for w are where? They're all over here, right? And so you could use inverse tangent of the imaginary part over the real part of w to define the angle there. And there's no jumps. So there's a single argument function that can be continuously applied to the 1 plus h over f function, where z is being taken from the boundary of D. Right? Yes, exactly. Well, yes, yes. Let's see here. But it's better than that. I mean, we can even use the stupid inverse tangent function, right? I mean, it's even lazier than just the principal argument. Anyway, the other thing to notice is that if we look at the argument of f of z plus h of z, it's equal to the argument of f of z plus the... Now, why is this, guys? Do you guys understand why this is? Where is this coming from? This is like way, way back. It's been a while since we talked about this, and it always makes me nervous to actually test on it because I hate to see what students do. I mean, I want students to understand it, but I just don't want to grade it. I'll be honest. Like, it is such a drudgery for me to check on whether or not you guys can actually prove that properly. Because this is a statement about sets, right? So to prove that properly, you have to prove the left-hand side is a subset of the right-hand side and vice versa. That's pretty much the only way to carefully prove that assertion, right? It's a set theoretic identity. And that's what's being used here. Well, actually, it's not that either, is it? This is actually, this is generally true, but we can say this, when is this true? This is actually what we need, isn't it? And maybe I shouldn't use Z and W, maybe I should use like A, B. I'm going to use alpha, beta. So what conditions do I need on alpha and beta to have that be true? Because I have cautioned you earlier in the course that the argument of a product is not the sum of the arguments unless there are strings attached, right? I'm thinking of alpha as being f of z and beta as being 1 plus h over f. See, because we're taking the argument of this, and I'm not sure that's the thing. I'm debating what the logic is. I mean, I think this is true, but in what sense is it? Is this true as a statement about sets? Is it true as a statement about a single argument? I think it's a statement about sets. See, because there's no assumption that the argument of f of z itself can be given by a single argument function. It's this guy that's nice. All right, so yeah, I think it's neither, I don't know, I'm debating in what sense we should understand this equality here. I think it's a statement about sets, but this is, how can I say this? Well, whether or not I can say it, the sentences which follow, I think, are quite reasonable. So the change in the argument of this sum is just matched by the change in the argument of that piece, because this piece, if you go all the way around the boundary of D, you come back where you started, and a single argument, the principal argument will give you the angle for that all the way around, so it just integrates to 0 when you come back to where you started on the boundary of D. And you just get this, right? But then, since the change in the argument of this is equal to the change in the argument of that, it follows by the argument principle number 2 that they have the same number of zeros. since by assumption there are no poles, we assume that, the assumption was that the function is analytic in this context here, so there's no poles. And that's it. That's Rachet's theorem. Now, so here is a attempt at a picture. Let's see here. What are these pictures? The red curve I'm thinking of as the image of f of z for z in the boundary of D. By the way, the boundary of D is not pictured. First of all, keep that in mind. So the red curve I'm thinking of as being the image of f of z under the boundary D. Let's see here. The green curve is the perturbation or deformation of the red curve. So h of z is actually pictured in here. The blue curve is the image of h of z as z is taken from the boundary of D, which is not pictured. Right? So h of z, as you can see, the image of h, modulus of h is always smaller than the modulus of f of z, right? It meets that condition. And the green is what happens when you add the, I tried to make a picture where the green is obtained from, well, actually, I mean, the thing that's lost in this is you don't know which points on the boundary are mapping to which points on these curves, right? So it could be that the point on the boundary of D is outputting this point in the f of z, but it might be outputting, I don't know, apparently it's outputting something like, I don't know, I'm trying to think of it, maybe make something obvious. This point in f of z, so then maybe we're adding that point in the h of z. So f of z plus h of z gives me that, and then back to there. Oh, I'm sorry, that back to there, something like that. I guess there would be a more complicated and perhaps improved picture where you actually took a specific boundary of D and plotted both the boundary of D, the image of f, the image of g, and the image of f plus g with a couple of points being tracked. That would be like an improved picture to see what's going on, but I've not seen that picture in a book anywhere. So was it the floatus or the floatus traffic that got you?
I had to go all the way back to east to get my stuff because we're on long range combo.
Oh, so it was the floatus. All right. Very exciting day for us all. I had to get my hair cut, just to celebrate it. But anyway, getting back to it. So it's given the terms and conditions here, it's clear that you can't get very far away from f with these conditions, and so you can see if f, I mean, in this case, in this particular picture, f is not 0, right? F of z is not 0 for z taken from the boundary of D in my picture here, right? And you can see why, in that situation, f plus h is also not going to be 0, right? Because it's like if you're walking on a path that's 10 feet from a let's say delicious plate of hot dogs, right? And you're walking your dog, and you've got a leash which is only 5 feet long, right? As long as you don't let the leash go, the hot dogs are safe, right? Because that 5 feet is too far to go away from the curve, which is at least 10 feet away from where the hot dogs are. And this is roughly speaking the idea, but all right, I'm going to go on. In fact, I'm going to go ahead and put this away for the moment and write out these examples because I think I should write them out. Come on. What's the what?
So, is the punctured disk a domain?
Is the punctured disk a domain? Is the punctured disk a domain? I think it's open and connected, so I would have to say yeah.
What's the boundary, and how do you integrate all the boundary of it?
Right. So I think that probably I should say bounded domain for Rouche's theorem.
What, is it not bounded?
The punctured plane's not bounded, no.
Punctured disk.
A punctured disk, sure.
Okay, so how do you integrate the
Um,
boundary of something that has like isolated points in the complement?
oh. Huh. Bounded domain with piecewise smooth boundary. I think the punctured disk just gets, when you're assuming that the function's non-zero on, there may just be like a special case to consider or something, I don't know. You're assuming that the function's non-zero on the boundary, right? So the boundary of the punctured disk would fill in that hole.
Oh, I see. So it's analytic on the boundary.
Yeah.
Oh, I see.
Yeah, it's analytic on D union the boundary, right? Yeah. Who is going to worry me after you leave, Sam? Let's see here. So example. Here we have P of Z, Z to the 11th, plus 12, Z to the 7th, minus 3Z squared, plus Z plus 2, right? And we want to analyze number of zeros within unit circle. So what do you guys, let's use Rouche's theorem. What should we make, what's nice? So for the nice thing, we're looking for, we want P of Z to be F of Z plus H of Z, where there are basically two things that we're kind of looking for here, right? The one is that F of Z is nice, and the other is that H of Z is small relative to F of Z. And the boundary of D here is, of course, just the unit circle, right? So what would be a nice thing to analyze the number of zeros of? 12Z to the 7th, right? So indeed, 12, how many zeros does 12Z to the 7th have inside the unit circle? 7, right? 7 zeros. In other words, as we would have said before, it has a single zero of 0 at 0 of order 7. And what's my H of Z? Everything else, right? Z to the 11th minus 3Z squared plus Z plus 2, right? Has modulus of H of Z less than or equal to what? Modulus of Z to the 11th plus 3 times the modulus of Z squared plus the modulus of Z plus the modulus of 2, where I'm using the what? Triangle inequality, right? And perhaps one other property, but anyway, those are all 1. So you can, for Z on the unit circle, we have 1 plus 3 plus 1 plus 2, which is what? 7, right? Thus, the modulus of H of Z is, so 7 So this is less than 7, right? And the modulus of f of z is equal to what? It's equal to 12 on z equals to 1. So therefore, modulus of h of z is less than the modulus of f of z for z on the units, or for z on the boundary of D. Hence, by Rouche's theorem, this 11th order polynomial has exactly 7 zeros in the unit circle. Yeah.
Is there a reason why it's just less than 7 for the modulus of h of z? Or like,
Thank you. Hmm. So anyway, I love this example. I think it's actually very powerful in its simplicity, because the thought of actually directly factoring that and finding those 7 zeros, wow, that's a mess. And yet, with very little effort, we have proved something that's quite technical. So it doesn't tell you where the zeros are exactly, but approximately it does, right? This is kind of an approximate method. It's an existence theorem, right? But it's also got kind of a calculational edge to it. Here's,
So we could use like polynomial division to find, like, choose other circles that are centered in places besides the origin, and then like find, like narrow down exactly.
yeah, that does seem like an algorithm. So your algorithm is something like just kind of take bigger and bigger circles. But I guess the trouble is, as you go out, you've got to, oh, you're saying use the polynomial long division.
Take smaller circles.
Smaller circles.
Places to,
So start with the unit circle and then zoom in,
yeah, on different places, and then pinpoint all the zeros.
something like that.
But this is probably something that only works when you have like one thing that has a coefficient that's a lot larger than all the others, right?
Yeah, I don't know. I haven't. I'm not versed in numerical methods for complex analysis. I don't know, but it does sound like there's something there that could be done. Yeah. Okay, so this one will give you a very different kind of example. Z plus 3 plus 2 e to the z equals to 0 has precisely one solution in the left half plane. This is the claim. And so the idea here is to find a function which has that as true, and then finding something else which we can look at as a perturbation, and hopefully we can find some curve or family of curves, right, which, and the limit as that curve gets really big, will fill the whole half plane and thus show the claim. And so the way we're going to do that is the nice thing, the f of z would just be z plus 3, right? We're going to let h of z be 2 e to the z. And so you can clearly see that we have f of minus 3 equal to 0, right? But that's the only 0 of f of z, right? So certainly in the left half plane, that's the only 0. And then what we do is we consider this, something like this here. So let's call that CR, and we're going from IR to minus IR here. Well, actually the other way, from minus IR to R, like that. And so I have just a few. Let's see here. So I said, if we can find a curve gamma which bounds the real part of z to be less than 0, and for which, so I said we want the So I'm replacing it. My goal is I want the real part. So you guys can tell me why this would be a good goal. The real part of z, well, that's just the left half plane, right? The real part of z is being less than 0, and we want the h of gamma of t modulus to be less than or equal to the modulus of f. Well, that's just the condition for what? That's just the condition for Rouche's theorem, right?
Should be strict.
Yeah, probably should be strict. Good point. I think a typo in my notes there. And that should be for all t in the domain of gamma, right? So then what I do is look at the two cases, right? What are the two cases for, and so I'm going to claim that this curve is going to do that. What are the, if we look at, sorry, I need to keep forgetting what I'm doing. If I look at z on the vertical here, right? Something like that, z equals to iy, right? For what? Minus r less than or equal to y less than or equal to r. What can we say about that point? We can say that the modulus of f of z is what? Looks like iy plus 3, right? And so what's the modulus of iy plus 3? It is the square root of 9 plus y squared, right? Or y squared plus 9 probably would be less weird. I don't know, whatever. And what about the modulus of h of z for these sorts of z's? Well, we got 2 e to the what? Iy. A real y, so this is indeed unimodular. I learned my lesson the other day. This is 2, right? Man, that confused me. So it should be apparent, it's quite clear, right, that 2 is less than, strictly less than, in fact, the square root of less than 9 squared plus y squared, right? Because 9 squared plus y squared is smallest what? What's the smallest value on the, yeah, 3 at the origin, right? So definitely we have met the condition of Rouche's theorem on the vertical segment. What about the curved segment? So I say, next up, we will look at minus, consider z equal to x plus iy in CR. So I say minus r is less than or equal to x is less than 0. Well, less than or equal to 0, I suppose. And we also have that minus r is less than or equal to y is less than or equal to r. Okay, great. So then I guess I'm going to use these to calculate the modulus of f of z on the curved part. Although it seems like I might be able to use the parameterization. I don't know. So the modulus of f of z is equal to what? The modulus of x plus iy plus 3, right? I'm going in some kind of silly circle here. In the notes, like I think I could write less here and get just as much out of it. I'm not convinced all these words need to be written. The bottom line here is that the modulus of f of z is what? I mean, it's the modulus of z plus 3, which is what? Distance from where? From minus 3 to z, right? And what's the modulus of h of z on the circle? On the CR? Two times e to the what? X plus iy, yeah? Which is going to be 2 e to the x. Because the modulus of e to the iy is just 1, right? So the magnitude of h of z is just 2 e to the x. And what's the largest that can be? Yeah, that is less than or equal to 2, where the 2 is attained up at the top point, right? Or at the bottom point. And for what it's worth, it's the perturbation is smallest when you're furthest away from the origin, right? All right. Can we see that 2 is less than, is 2 going to be less than the distance from -3 to z? Where's -3 in this picture? It's like here, right? And so if you look at -3 and you look at this curve geometrically, it should be clear to you that that's the closest point, right? So if we sort through the details of this correctly, that will pop out of the analysis, right? So apparently we need a condition on CR in order to be sure that we can apply the condition of Rouche's theorem, right? But we don't need this to hold for all possible half circles, right? We just need this to hold for half circles sufficiently large. Because if it holds for half circles sufficiently large, then we can apply Rouche's theorem on such half circles and we're good. So we just need to add what condition about R? Yeah, R is larger than 5, right? If we have R is larger than 5, then this distance, which I'll put in green shortly, is going to be what? Implies that D is what? Greater than 2, right? And if that distance is greater than 2, that means that the modulus of f of z is greater than the modulus of h of z on the boundary of the half circle. Therefore, since we can do this for arbitrary r larger than 5, applying Rouche's theorem, in each case, we see that the number of zeros for z plus 3 plus 2e to the z is just 1. Because that's the number of zeros for z plus 3 in the left half plane. Yep.
What if it's less than 5?
If it's less than 5, then I can't apply Rouche's theorem. Because we haven't met the conditions for Rouche's theorem for f and h.
So how do you know there's only one solution then? Like what if R was
Oh, because this has just 1 0 in the left half plane, and Rouche's theorem applies to it when r is greater than 5.
So we just make R bigger, and then eventually we get rootable.
Rouche's theorem does not hold for all r. So the fact that it fails for r less than 5 doesn't trouble us. It's just irrelevant. I have been where you are before. I feel your pain. Seriously, like I have spent a long time logically right where you are, and I know what you're struggling with. I don't know how to undo it for you. But the best way I can say is like we're applying Rouche's theorem only in this case. And you know, when I look at r equals to 6, it gets me, you know, like this half circle, roughly speaking, right? And then when I apply r equals to 10, it gets me this half circle. And I just keep going out and out and out. But I've already got this part of the half plane at 6. So I
you
just
don't really need the smaller ones because when you go bigger, it already includes all.
exactly when we go bigger, we've already included the smaller things. We don't. Yeah. Yeah. Okay, so let me get the projector back out again. Mm-hmm.
So if an example like that, if you had something where it was like the quadratic part of it that you knew that
I think it's very possible. I think that there's no possible way I could even describe all the possible different uses of Rouche's theorem. It's like trying to explain how many different ways there are to use a hammer, you know? That's a bad analogy. Everything with a hammer looks like a nail. But it's like more like a Swiss pocket knife, I would say. I don't know. Stupid airport. Anyway, yes?
In the example, in a non-linear wind, unfortunately, it's the right half plane. So when over there, it would be zero, x is between 0 and r. So I don't know when x is between 0 and r, how do we, the modulus of h, z, how do we define that the modulus of h, z is less than something when x is positive?
Yeah, I don't know. I don't know how to solve modifications to this problem off the top of my head. I'd have to sit and think about it. But what I want to show you now, you can ask me more later, but I won't be able to answer your question at the moment, James. I'm sorry. I mean, reasonable question, right? But the right half plane is troublesome though because the exponential is not bounded in the right half plane. So. What do you try? Are you asking about a homework problem or?
I think the homework problem is the right half plane.
It's the right half plane, but it's e to the negative z.
Oh, e to the negative z.
Oh,
Woohoo! E to the negative. So the same. Well, if I say much more about it, I'll solve the problem.
Also,
Yeah.
I solved it without Rouche's theorem because I did it before reading that section. And I was like, oh.
So it's actually not a bad problem even without Rouche's theorem.
Well, if you don't have any basic skills.
Curses. Well, this is the thing that, you know, the skills of the undergraduate student should not be ignored. I mean, oftentimes I give us like a research problem to an undergraduate with the hope of them like thinking hard about how to generalize my stuff, and what do? They just take a series, they plug it in, and they just do a horrible calculation, and then they get it. I'm like, I mean, it's not wrong, but it's not what I'm after, right? I mean, in some sense, like calculus too, right? Why teach partial fractions, trigonometric substitution, integration by parts, all these things, right? Forget about all that nonsense. You teach them series, day one, right? And then how do you integrate? You take your function, turn it to a power series, and integrate term by term, and just do that. Because then you can integrate everything pretty much, right? I mean, but then the answer is the series, right? So it's a question of what you're after. This, ironically, I think is easier than the two examples I've showed you today, in some sense. So take an arbitrary polynomial of order n, a n z to the n, a n minus 1, z n to the minus 1, da 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 dot, a n not equal to 0. Let f of z be a n z to the n, right? How many zeros does that have? N, right? At 0. And your perturbation, the n minus 1th order polynomial, that, right? Certainly p of z is f of z plus h of z. And if we make r sufficiently large, it's pretty clear that you can make the modulus of h of z, which is less than or equal to this n minus 1th order polynomial. You can make that smaller than r to the n, right? This is just basic inequality figuring, right? If you've got something squared versus something cubed, if you make something large enough, the cube is going to win big time, right? I mean, if you have a higher power to work with, you can make that dwarf this after r is sufficiently large. I think that's much easier to prove than that horrible homework problem we had earlier, where we proved the fundamental theorem of algebra using Liouville's theorem, right? The inequality required there was much more delicate, and the proof was by contradiction. The proof I'm describing to you right now is direct. So we can see that the modulus of h of z, the next to leading order part of the polynomial, is less than or equal to the modulus of the leading order part of the polynomial, right? And so by Rouche's theorem, on this circle of sufficiently large radius, the number of zeros for f, which is n, is equal to the number of zeros for p, which is an arbitrary nth order polynomial with complex coefficients. There you go. Proof of the fundamental theorem of algebra. This is by far the cleanest and most elegant proof I will show you of it. I like this one. This is, I think, the perfect place to stop complex analysis. So, yeah. Now, there are dozens of other topics at your level that you could learn. Open mapping principle, Schwartz reflections, further conformal mapping. There's something called Runge's approximation. It is about approximating functions with sequences of polynomials. There's the whole discussion of like Julia and the Mandelbrot set, all that stuff, complex dynamics. There's using residue theorems to calculate series. You can calculate series with residues. You can extend partial fractions to infinitely many partial fractions. Right? There's a quote-unquote partial fractions decomposition of sine of pi z over z, where the number of singular terms is infinite. So there's like a generalization of partial fractions. There's things you can do with infinite products and their relation with infinite sums. This is also Mittag-Leffler and the Weierstrass product function stuff. I mean, there's a lot more out there that I've not touched on, that I have touched on in previous semesters. All right, but you can't do everything at one semester. And I just want to let you know that, this is where we're stopping, but there's much more to learn. I've not even scratched the surface of several complex variables, and there is hard stuff in there. Now, so let's talk about the integral. So I'm changing gears here. This is my introduction to a calculus paper, and the last section in it is, oh, come on. Dang it. Go away, you. All right, here we go. The last section in my A calculus paper, which is intended as a primer, eventually this is going to become a book, I would hope, hopefully at your level, give or take. And so obviously you want to understand how to do integration over an algebra, right? So I will send you a link to this at some point, but it's already posted, like at the top of my website, on the papers that I've posted on the archive. It's like right there. I just want to, so my goal for today is just to share with you the main definitions and what I've already shown. All right. So I may inadvertently show you a solution to one of your homework problems here. I probably shouldn't even show you this. All right, I'll risk it. So I want to describe how to integrate functions. So I start by describing how to integrate functions from the real numbers to the algebra. So this would be like integrating a complex valued function of a real variable. How do we do that? We integrate what? The real part and the imaginary part separately. This is just calculus 3, where you learn to integrate a space curve. You integrate component-wise. This is just that. So I integrate component-wise. And you get linearity. You can pull out the algebra multiplication. You get a fundamental theorem of calculus at that level. The proofs are all through like structure constants, and it doesn't matter. Then to define the integral, of a function on the algebra, what I do, so the integral of f of zeta d zeta is to start with, just use this sort of generalized Riemann sum. All right? And through almost the same discussion we had in here about how to go from the Riemann formulation, the complex integral, to the parametrized formulation of the complex integral, that same thing holds for this integral. You can reformulate it as take your algebra function, evaluate it, the parameterization, multiply by the derivative of the parameterization with respect to time, integrate over the appropriate domain for the parameterization of the curve. That gives you the the algebra integral. Same thing. And you haven't, you guys have been used to using the ML theorem in here, right? Most of your homework right now is somehow anchored on that. Well, for the algebra, we have a mammal theorem because that's the submultiplicative constant that appears. again, this is the theorem I was just indicating with words. To calculate the integral, you can actually just parameterize the curve, take the function, evaluate the parameterization, do the algebra multiplication of the derivative, and integrate over time. It's what could be more simple than this? I mean, it is exactly what we do in the complex case, just with complex multiplication being replaced with algebra multiplication. So here's the hyperbolic integral. If you look at f d zeta dt, so letting f be u plus jv, and d zeta being dx dt plus j dy dt, multiply this thing through, you got that and that. And so if you integrate this over dt, just using the usual differential notation for like integrating dx and integrating dy, like we teach you in Calculus 3, right? The usual differential integrals. We have that f of zeta d zeta integrates u dx plus v dy plus j times v dy plus u dx. So intuitively, really all that's going on is we have z is equal to x plus jy, and so dz is dx plus j dy. So if you're integrating u plus jv dz, you just multiply it out using that j squared is 1. So it behaves just like the complex line integral, right? Which I was very happy when I learned this. It's just, what could be more natural? It's just a simple extension of what you've already learned. There's a chain rule for compositions of a-differentiable functions and parameterizations of a curve. This is the chain rule. So you take the derivative of the a derivative of the function evaluated at the path times the velocity of the path, like that. And because that's true, that ends up giving us the that theorem. It also, as a side consequence, allows us to prove, oops, this is what I shouldn't show you. Actually, this is not even the proof I intend for you guys. I have a different proof in mind, which I'll try to indicate to you next class, I think, because I think we're out of time. But here's a proof for FTC2, right? So you take the integral, convert it to the parameterization, look at that instead as the derivative of the antiderivative at gamma of t, and then by fundamental theorem of calculus for complex valued functions of a real variable, we get that. So, but I have in mind a proof for you guys where you just use the Cauchy-Riemann equations to manipulate it back to like integrals of total differentials. I'll try to, which is the same proof that I was encouraging you guys for the test in here. Like the proof for FTC2 in the test was based on using partial f partial y is equal to I partial f partial x. So if you do that level of notation for the algebras Cauchy-Riemann equations, you can mimic that proof in the same way. But anyway, we're out of time, so I'll stop. But